one of the co-organizers of the workshop, so thank you so much, Yadang. He's a final year PhD student in the EECS department at UC Berkeley, advised by Mike Jordan and Yima. His current research focus are broadly in theoretical foundation and applications of trustworthy machine learning, specifically optimization and uncertainty quantification for collaborative and federated learning, and also building differentially private foundation models and interpretable deep neural networks.
Thanks. Thanks, Pranith. Can people hear me? Yeah, I can hear me myself well. Hi, everyone. Hopefully you have a nice lunch break. So I'm going to share some of our recent work on federated, like how to do rigorous conformal prediction in the federated learning setting. So this is a joint work. This work is co-led by Charlie and his advisor Ramesh, and joint work with Praneeth and Mike here. We also have here's a paper link, and we also have the GitHub repo online. Feel free to play with the code. Cool, here is the outline for this talk. So I will briefly mention why we need uncertain quantification, as several speakers already talked about earlier this morning. And I will give a brief overview of basically a 5 minutes introduction to what is conformal prediction, and then go to our method, how to do conformal prediction in the federated learning setting, and show a few experimental results. In the end, I will conclude with a few future directions. By the way, I think actually several speakers in the room, they also working on similar topics. Eric has a paper on label shift in the federated learning setting, do the conformal prediction. And Jashri with Charlie also have some very early work on the evaluating conformal prediction in the federated learning setting. Cool, it's a very exciting direction to work on. Cool, so before we go, let's first start recap the setup of the federated learning scenario. So I will quickly go through. Suppose we have capital K number of clients, and every client we want to minimize. In front of each client, we have weight in front of each client, and the standard or most of the FL algorithms are focusing on how to learn a good predictive model from these collectively from all the capital K number of clients. So given this F hat, this predictive model learned, what we can, what usually people do is given this test input X and go through this model and get the output, which is F hat X. And then just as a lot of deep learning models are operated, just take the argmax of the output and then make the prediction, which here is a point prediction, which is a dog. So what's missing here? So as Mike alluded earlier this morning, and Alan also talked about the uncertain quantification. So in the classical statistical learning or statistics, instead of just to give a point prediction, you also want to give an interval, so a confidence interval. So at the first row, I'm showing a few regression examples. Instead of just predicting what the F hat is, you also, at each point, you want to give a confidence interval, say how likely this prediction will lie in this band. And the second row, I'm borrowing some slides from Anastasia's, is for prediction the classification problems. Instead of just give a point prediction which class this image is, you also want to give a set instead of just a 1 point. So how do we modify the current pipeline to make the output to be more could provide some nice uncertain quantifications overall for this pipeline? So from the previous one, instead of give a point prediction, we can give a prediction set. This C capital hat C, this function is a set valued function given input X. It will output a subset of the possible output space Y. So what's nice about this is, or what's nice about conformal prediction is whatever the black box model, like it could be like arbitrary, like either from linear regression to like say deep neural networks, and regardless of what's the data distribution, you can build some types of rigorous uncertainty using conformal prediction to like make your predictions or make the model predictions to be more reliable. So that's the motivation part. I will go give a very brief overview of what conformal prediction is. So this talk, for simplicity, I will focus on like the split conformal. There's different variants of conformal prediction. So here, suppose we have a training data set D1. We use D1 to train our model, just whatever the favorite model you want. And given the f hat, we use another data set, say the calibration data set, D2. Given D2, we, together with this point predictor, we can use conformal prediction to get a set value like a predictor, which is C hat alpha. I will introduce what kind of guarantees this C hat alpha could have. So just set up the notations a little bit. So given a distribution P, we can sample n number of data points, n number of data pairs, xi, yi, and suppose we consider the classification regime. We have capital L number of classes, which denoted by this capital Y. And what conformal prediction could provide is, given we can construct a set valued function, which is C hat alpha. Given, suppose we have an IID pair in the future, xn plus 1 and yn plus 1. Suppose that's a test data point sampled. And then what C hat alpha like have this guarantee is, the C hat alpha, given this xn plus 1, it will provide a set. And the actual label will belong to this set with high probability. So basically, this alpha is some parameter you can set. For example, you can put alpha as 0.01. Then suppose you have a reasonable large number of calibration data points. Suppose small n is 1,000. Then you could, like, by learning this or constructing this C hat alpha, you can get a reasonably like pretty good calibrated like predictor that such that with high probability you will provide a prediction set and the actual label belongs to this set. So that is what like conformal prediction could have. And the nice thing of conformal prediction is you don't need to assume or make assumptions on the data distribution nor on the predicted model. So the model could be arbitrary and the data distribution could be arbitrary. And it also has a finite sample guarantee. So basically, the number of samples you have, the small n, if n is 1,000, you can treat this small error term to be super small. So that's the nice part. And I will work through like a very simple example how you can construct such like conformal prediction predictors. So given n number of samples, we can construct a score function which is S. Here we are taking like the LAC, which is an algorithm in CP. We just take the yi's coordinate from this probability vector and 1 minus this value. And then we can compute this value for each sample. And then we compute the quantile of the n number of scores. After that, after computing the quantile, which is Q hat, then we will like use this Q hat for future predictions. So basically, suppose I have an X test sample, I just evaluate each label, each small y label, whether this label together with this function is below this Q hat, and then I will construct a set which contain all the y's that is smaller than this value. And I just give a very one-page like picture proof why this works. So the assumption is IID or the data are exchangeable. So suppose I have n number of values. What you want to do is you compute the quantile of these n number of values. There's a collection term here, a correction term there. And like, suppose yn plus 1, which is the score, is exchangeable to all the previous n number of data points, then like, it's very likely this will lie into this 1 minus alpha fraction, that it will give you the correction prediction set. And this is borrowed from Ryan Shani's slides. Okay, cool. And how do we evaluate whether the conformal predictor, like the performance? The first thing is whether this conformal predictor could give you the set that actually cover your actual label, which we refer to as a coverage. And the second one is the efficiency, because you can always construct like a prediction set that whatever x you give, I just output the whole white space. And that does not make like much sense. You want to make the prediction set to be as small as possible. So these are the two criterion that like to evaluate how like CP is. And for more examples, not only the classification problems, it can be applied to a wide range of problems. Yeah, I highly recommend to go to Anastasia's and Steven's tutorial, like on like what kind of applications this conformal prediction could be applied to. And next, I will introduce how we construct this federated conformal predictor. So first of all, we have, suppose we have still capital K number of clients, and we use these to train a model F hat. And we consider for each client, we have nk, like small nk number of data points from this particular client. And then the test distribution we are considering is a mixture of from P1 to PK. So the test distribution we denoted by like this Q lambda, like basically is a linear combine, or this lambda is lying in the simplex, is a linear combination of, the Q test is a linear combination of from P1 to P capital K. And we are considering a test data point sampled from this mixture. And given these data points from this capital K number of clients, we want to build a conformal model that works for this Q-test distribution in the future. So the overall goal is, given nk number of data points sampled from each client, we have capital N number of like calibration points collected from all the clients. And then our goal is try to build a set value function, a conformal predictor, such that still achieves similar like coverage guarantees as we saw before in the centralized case. So what's the challenging, or what's the challenges here? Why can't we just directly apply the standard like conformal prediction techniques in this scenario? So the first challenge is in the previous slides, I showed like there's some IID assumptions. So basically, you assume the n+1 data points are exchangeable to each other. However, here you can think within each client, the data points are exchangeable, but across the clients is not that exchangeable. Consider one patient probably could go to like multiple hospitals at the same time is highly correlated, so you cannot actually make the exchangeable assumption across the clients, or putting this capital N number of data points together is not exchangeable at all, or is not exchangeable anymore. So the second challenge is data heterogeneity. So basically, because there's also optimization happening here, so you cannot actually take one client's data to construct a conformal predictor and apply it to everyone else. So here in the left, we show that if you do that, you actually got some under coverage. Your desired coverage is 0.8, but then your actual coverage is way below 0.8. So like also there's a heterogeneity effect, like if your model like not optimized pretty well, so you have very large prediction set size, which makes the conformal prediction not that effective. So how we deal with the challenges here? So we first identify what's the right assumption under this scenario. So here we are making the assumption that the data points basically essentially are partial exchangeable. So what do I mean by this? So given the test data point, we are assuming the density function can be decomposed by a mixture of k number of density functions, and lambda k is the lambda we used in the previous slides. And here you can think that instead of exchangeable across all the data points, that within each group or within each clients, the data points are exchangeable. So it's kind of partial exchangeable. And by leveraging this, figure out what's the right assumption, we actually could build the conformal prediction relatively easy. So basically, we compute the Q hat as that n plus k multiplied with 1 minus alpha quantile. So after selecting what's the right quantile value, we can construct this distributed conformal predictor that satisfies this nice coverage guarantee. And on the right-hand side, it's slightly different from the right term, the term we saw in the centralized case. And if we set k equals to 1, then we can reduce to the centralized case. And the pipeline is we have a prediction model, and then we can apply this FCP to wrap up our model as a conformal model. And during the test, we can predict what's the prediction set for this particular test sample. And besides the setting I described earlier, we also have several extensions, like what happens if your lambda is shifted from the one you specified, as well as suppose the Q hat cannot be computed exactly, suppose it's approximated, or if we adding some Laplacian noise to get some privacy guarantees, those can make the Q hat not accurate. We also covered those settings, but I will skip for this talk. And let me quickly go through some evaluations. So here we saw that we can actually build some conformal predictors with nice coverage guarantees. And we also found that the optimization algorithms you applied really matters a lot in this setting. So basically, the more accurate the model is, the better the smaller the set is, or the better the conformal prediction model is. And actually, our previous, more like an advertisement for our previous algorithm called train convex and train. I joint work with Praneeth and Mike last year's NeurIPS. This is more like convex-fied approach, try to tackle the data heterogeneity challenges. And this conformal prediction algorithm could also be applied to do more some other applications like selective classification. So basically, suppose the prediction set size is small, then it is more likely to be accurate. So if we pick the predictions or make more accurate predictions by just making predictions on those with small set size, then we have pretty high accuracy. And then if we don't do the selective prediction, the accuracy is pretty bad. And the last one is we can also use the set size to compute whether, basically the larger the set size is, the predictions are more likely to be inaccurate. So this is a relationship between the accuracy and the set size. So larger, the worse accuracy. So that's all the experiments or evaluations. We have more results in our paper. Feel free to check that. And some future directions, which is quite related to today's earlier talks. First one is how to do more personalized conformal predictions. So here we are more considering a centralized model, how we deal with the future data points sampled from the same distribution, how to adapt to each client. The second one is suppose a new client joined and the client distribution is also shifted from the previous ones. And the last one is how try to extend this framework to more complex tasks like segmentation, multi-label classification, detection, all kinds of applications there. So I will stop here and thank you.
Any quick questions while short form set up? Please, go ahead.
Maybe it's good.
Yeah.
Yeah.
Okay. Thanks, you're done. Dr. Shaw Lee, hope I got the pronunciation right, is an assistant professor at University of British Columbia and an adjunct assistant professor at Yale Medical School, faculty member at Vector Institute. She specializes in enhancing the trustworthiness of AI systems within healthcare through her leading leadership at the Trusted and Efficiency AI Lab. Her work has been recognized with numerous publications, and awards. She develops theoretical and practical solutions for, sorry, I'm repeating myself. Her research directions has been dedicated to advancing federated learning techniques and their applications in the medical field.
Yep. Maybe just share the presentation.
Yeah, we just need to share it on Zoom.
But it's
Okay, can I have it on the screen? I can. Okay, can I have it on the screen?
I just realized it was not corrected the type. It's not fixed. Yeah. I don't know why it's not saved.
It's okay, it's okay.
Maybe.
I'm not sure. Am I? All good? That's not sharing.
Oh, meanwhile, there's a panel discussion at 4 p.m. If there's a topic which any of you is particularly motivated to, present to the discussion, let me know. Yeah, or any question which you think we should talk about.
Okay, cool. Yeah, no problem. And sorry for the technical issue, and thank you for waiting. It's my honor to be here, and this is my second time to come to Middle East. My first time was in 2016 in Qatar for the World Cup. So still feel very excited for the weather and the food here. Today I will share our work about overcoming heterogeneity challenges in federated learning. Different from the style that Yaodong and a few presenters did earlier, I will not focus on one single work. Instead, I will give a gallery of some related work. And thanks for the earlier speakers have set up the good foundations of introducing the notations, and I will directly go to the methods. Oops. So we know that AI has shown its power in many tasks. For example, the ImageNet classification challenges and the segmentation tasks. So those amazing results are typically achieved using the natural image data. However, when we look at the real-world data set, for example, medical imaging, that's what I trained from. I work on neural imaging during my PhD, but still I'm working on different types of medical images. We found that the real-world decentralized data actually are not ideal. They suffer from the heterogeneity issues, such as feature shift. We have the MRI scans for brains from different centers. As you can see, the pixel densities are different. And we may also have the label shift issues, namely the class prior distributions can be different for different centers. And we also have different sensors that cause different data collected. When we look at the heterogeneous data, some issue may occur. So these are two figures from the original Fed average paper. The conclusion is here. Convergence to the optimal model can be typically guaranteed to the IID data. However, issues arise in strongly non-IID data. And in order to do the optimization of federated learning on heterogeneity, a traditional way is to optimizing a global model, such as this is a figure from Scaffold, which analyzed the training trajectory from two heterogeneous clients. And this paper suggested that we will have the client drift issue, particularly when you use a very large local update epoch. So in order to ensure the convergence when you're optimizing a global model, people typically require small local updating epoch or adding some regularization. Both strategies can slow down the convergence. There are another strategy called personalized federated learning. We have heard about this terminology many times. So this allows different clients to learn a little bit different models. For example, part of the model parameters may be shared and some are different. In this case, we need to design some objectives for them separately, but still enforce them to collaborate. Next, I will introduce our field work, how we leverage personalized models in our setup. So skip a few slides. Okay, so the first work I want to introduce is FedBN, federated learning on non-ID feature via local batch normalization. Maybe some of you have heard about it, and this paper was published several years ago. Here we focus on the issue of feature shift. Mathematically, we define the definition as follows. So our proposal is as follows. Compare with the original Fed average where you share all the model parameters. Here, we suggest all the clients keep their batch normalization parameters locally involved rather than averaging on the server. This is very easy to implement. You only need to change the aggregation strategy. We have the toy example to show that if you only averaging the non-BN parameters, you will have a much lower generalization error in this toy example. We also did the experiment on the benchmark data set, and as you can see, compared with some other methods, we can perform the best. This is the old comparison, and I know people now use FedBN for new data sets. Some of you may notice that FedBN cannot achieve good performance, but later when we examine the data set setting, they use FedBN for the label shift setting. Here is more like a clarification. We show FedBN originally, particularly for the feature shift issues. Another interesting phenomenon we observe is that FedBN actually can converge faster than at Fed average. So this figure shows the learning curve for FedBN in the solid line and the Fed average in the dashed line. We have the zoom-in version here. As you can see, the solid line is underneath the dashed line. So we also conducted a theoretical analysis, which is based on our Fed NTK work. We calculated the kernel matrix for Fed average and Fed BN. We found that the smallest eigenvalue of the kernel matrix of Fed BN is equal or greater than Fed average, the equal sign achieved when you use the IID data. So in this case, we theoretically justify why Fed BN can converge faster than Fed average. So as you can see, a simple strategy by personalizing the patronization layer can boost the performance of federated learning on heterogeneity data. In addition to the feature shift issue, we also look at the label shift issue. There are many work addressing the label shift issue, but here we are dealing with a more challenging setting. Here are the practical scenarios that we're looking at. The class priors or label distributions are different due to the demographics. And also, we consider that if we set up the federated learning across hospitals, the hospitals may hold unlabeled datasets, in short, USET, due to the absence of the budget or the expertise. And nowadays, when we talk about privacy, we can also claim that hospitals don't want to share instance-wise labels. Here is an example that maybe one hospital only want to report that 85% of the population, they are healthy control, and 50% of them are patient. For another hospital, they may claim that we have 90% of the healthy control and 10% of the patient, and so on. So given such a setup, can we train a classification model to classify each instance as a patient or healthy control? To this end, we leveraged the unlabeled learning strategy, which was developed in centralized learning and adapted into this label shift issue. So firstly, for each hospital, we randomly cluster these data samples into M sets. So these M sets formulate this surrogate task. We use the index of the unlabeled sets, in short, U sets, as the surrogate label, and then perform the traditional Fed averaging to do this surrogate supervised federated learning task. Now the question is that, given this surrogate federated task, how can we infer our desired classifier from the surrogate federated learning task? In our paper, we bridge the class priors between this surrogate task and our desired task as follows. Suppose the true class probability is defined as int C, and the surrogate class priority is defined as this dash int C. So we show that these two probabilities can be connected by a transition matrix QC. And see our theory 1 for details. Then what this QC will be used for in our case? Let's go back to the traditional federated learning setting for the surrogate task. We have to train a neural network. And then we just add this QC, suppose we know what QC it is, onto the output of the neural network. So this QC can serve as the personalized layer to fit the shared models into the heterogeneous label distributions. And what is this QC? We show that QC actually can be calculated from the class priors. But in practice, the class priors cannot be known in advance. In this work, we assume that we know it. So following this work, we consider a practical setting that we have some information for us to estimate pi c. In this case, we assume that the server may have a small amount of data, labeled data. However, all the clients, they have the unlabeled data. And also, their label distribution, the underlying label distribution, is heterogeneous and imbalanced. To retrieve this, the first step will be estimating the class prior. We following the traditional pseudo-labeling strategy. First, we build a dynamic bank and then try to calculate the pseudo-labels. We don't count in all the samples. Instead, we consider the confident samples. But that's not sufficient. If you consider the invariance data, different class may have different confidence score distributions. So in this case, we actually use two different thresholds to encourage the minority classes also can include some samples in the dynamic bank. So we can estimate the class priors better. Once we obtain the class prior, we formulated such a semi-supervised learning problem as follows, which is a combination of the supervised learning loss on the server data and the unsupervised learning loss on the client data. Given only a few minutes left, I want to introduce our another recent work where we discussed the device heterogeneity. Different devices have different computational powers, so we have to customize the model structures to fit in their capacity. So in this case, we follow a strategy called pruning, or in another word, we mask out some parameters so that for some device with smaller capacity, we train less number of parameters. Then the question comes to how should we design the masking vectors? Here we divide the model into two parts. One part is the body model, which is the big chunk of it, and another part is the head model, only a few multi-layer perceptions. So on the client side, we say that let's apply this masking vector onto the gradient of your updating that fit your capacity. And on the server side, when you do the aggregation, so you calculate this normalized masking vector and then put onto the aggregation step. In addition, we say that the server needs to determine the best masking vectors following this additional optimization objective. Why we have this term? This because we conducted the theoretical analysis and found that we have this additional bias term in our convergence bound. So we want to minimize this additional bias term. In addition, after training, the personalized model will be fine-tuned based on their local data. And more recently, we claim that personalized model may not be the best solution. We found that there will be a trade-off between the personalization and the generalization. And here's why. So in personalized federated learning, we focus on the local performance, so you get the lowest loss based on your local testing data. However, when we check the global loss at this local optimal parameter, it may have very high global loss. So our proposal is that, can we have a sweet spot, which is in this yellow star? Well, we may not get the optimal for your local loss landscape, but at this point, we have a relatively low local loss and also a relatively low global loss. In this case, we have a good trade-off between your personalization and generalization. So how can we achieve this? We modified the widely used local fine-tuning strategy in personalized federated learning, motivated by the model soup work. Model soup is a model ensembling strategy that improves the generalizability of your neural network. So for each client, we use their validation data to select some global model. Noting that in the traditional personalized federated learning, you only focus on this last round of global model and then do fine-tuning. But in this work, we say that let's collect more ingredients to make a better soup. So for each local model, we look at all the global model trajectory and then select the good ones. So when we do the local fine-tuning, in addition to the fine-tuned model, we also perform further interpolation with the selected good global model. So in this version, we found that we can improve the generalizability while didn't decrease the personalization performance that much. Some ongoing work, we try to make the soup better and more delicious. So my student proposed that let's make more richer ingredients in the local model by performing some random masking. So in this case, when you do the local fine-tuning, you can generate multiple local models by random masking strategies. As the preliminary results show here, when we performed 80% of sparsity pruning, we can achieve much better performance than using unpruned local model. this is pretty much of my recent work on tackling the data heterogeneity issue. I want to say acknowledgement to my collaborators and my fantastic team at UBC and my funding agency to support all this work. Thank you for listening, and here's a quick overview about our work and then touch from these different regions.
Any questions? Maybe I can ask one question about the, you mentioned that I guess you mentioned the global performance as like a proxy for generalization. Can you talk a bit more about why that's a good, like doing well on the global laws was the connection to that with generalization?
Yeah, so the question is about why we link the global laws to the generalization. I have to say that's not the exact link. For here, we assume that actually if we consider some kind of like testing data, like what Yaotong earlier mentioned, it may be a linear combination of the local distribution. So in this case, when you look at the global loss, you can approximate the generalization performance. Yeah, that's a great question.
Oh yeah, there's a question at the back.
Hi, thanks for the talk. My question relates to concerning the intersection of masked models when you're doing the Fed soup. Do you have any insights on what coverage you should have over an aggregation round? Like how much coverage you need to have across different, let's say, paths or sub-models that you're aggregating?
Yeah, so if I heard correctly, you are asking how many models did we use for the ensembling or interpolation? What's the question?
Yes, or the intersection of these models, how much of the actual model it needs to cover in order to work and converge?
Yeah, so in our case, we use around 3 to 5 models in the first version. But in the second version, so we do the hierarchical interpolation. So when we have the diverse local model, we do the first level of interpolation. In this case, we typically use 5 to 10 local model. And then in the next step, when we integrate with global model, we didn't increase the total ensembling models. Yeah.
Great, thanks.
But actually, that's a more heuristic hyperparameters. Maybe for different data sets, you need to choose a.
And this is cross-silo, is that correct?
Sorry?
This is cross-silo setting.
Yes, for our experiment, we assume the cross-silo settings.
Okay, great, thanks.
Yeah, thanks.
We next have Karthik Nandakumar. Karthik is an associate professor of computer vision at MBZUAI, and before this, he was a research staff member at IBM Research in Singapore. His primary research interests are in computer vision, machine learning, biometric recognition, applied cryptography, and blockchain. He's specifically interested in developing secure, privacy-preserving, and trustworthy AI systems. Karthik is also one of the local hosts for this workshop. Thank you, Karthik.
Yeah, thank you, Sai, and welcome all of you to MBZUAI. So following the previous speaker, I will also introduce a cluster of 3 topics instead of focusing on a single problem. So my work, as I mentioned, is mainly about secure and trustworthy AI. And in this presentation, I'll be mainly talking about some of our work in improving the robustness, privacy, and fairness of collaborative learning. Okay, as you all know, collaborative learning, where multiple entities collaborate with each other in order to achieve a more accurate or more useful model. And the key premise is that they don't share the raw data, right? So that is the core premise of collaborative learning or federated learning. And one of the common assumptions is all the clients are honest but curious. So basically, they want to find out the data about other participants. It could be the clients or the server. They want to find the data about the other participants, but at the same time, they want to reveal as less information as possible, but they honestly follow the protocol. And as Mike introduced in the morning, there's a federated setting where you have a central orchestration, or you can also have a completely decentralized collaborative learning framework where there is no central orchestration. It's just all the clients directly talk to each other in a peer-to-peer fashion. Right, so my work is motivated from concepts in biology, right? So basically, if you look at nature, right, when people or organisms or species collaborate or live together, there are various possible types of collaboration, right? So one is, the most common one is mutualism or symbiosis, which many of you might have heard about. So this sea anemone and jellyfish, where both the organisms kind of benefit from each other by living together. But that is not the only prevailing principle in nature, right? So there is other things like commensalism, where one organism benefits, the others don't get any benefit, or at the very least they are not harmed, right? And then there is parasitic behavior, where basically there are some species which try to live by essentially harming others, right? And finally, you have a competition kind of scenario where different organisms are competing with each other for the same resources. So basically, my goal is to develop collaborative learning algorithms for this non-mutualistic scenario. So when there is communalism, parasitism, or competition. So how do you handle these kind of scenarios? So basically, it boils down to three main problems. So one is, instead of just focusing on accuracy and efficiency, you also need to look at things like Byzantine robustness, which Samuel introduced in the morning, right? So you have algorithms which should be resilient against selfish behavior by malicious participants. The next thing is what happens if the privacy is compromised. So most of the federated learning algorithms, they just focus on data confidentiality. The raw data is not shared, but some updates are shared, and that might leak sufficient information about the raw data. So how do you prevent this leakage? And finally, the issue of collaborative fairness comes in, which again Mike alluded to in the morning, right? So you need to have proper incentives for collaboration, and these incentives have to be fair across different participants. So how do you ensure these three properties will be the focus of my work? So the first problem I'm going to address is about Byzantine robustness, where you have clients, malicious clients, which are trying to subvert the learning process by introducing poisoning updates. Right? So how do you handle this kind of scenario? So one of the works that we proposed is, okay, so you have updates, you have a server which is trying to aggregate updates from different clients, but then the server can compute either directly from the updates, they can do some kind of clustering, which is the main focus of the previous work, and they can try to find out what are the outliers in those updates. Right? So that is one possible approach. But in this work, what we do is finding these outliers is very difficult directly in the model space or the update space. So what we try to do is try to compute distances or similarities between these updates, and then try to find the outliers in this distance space, which seems to work much more effectively than directly trying to find the outliers in the update space. So this is one example of our work. So where basically we show that, so in this case, the first one, there's no attacks, like all the clients are honest, right? So in this case, all the clients contribute to the learning process, and it works as well as federated averaging, which is the most common aggregation approach. But in cases where, let's say, some of the clients are malicious, right? So in the second example shown here, you have a 10% label flip, which means like one of the clients is malicious among the 10. So in this case, we are able to clearly identify the malicious participants even in the very early rounds of collaboration, and then kind of suppress their updates so that they don't affect the learning process. And we can do this across different types of noise and different number of malicious clients. It does not have to be one client, right? So you can have up to, let's say, close to 50% of the clients can be malicious, and we can still continue with the learning process without any problem, right? So as long as the majority are honest. Okay, so the next work I'm going to talk about tries to address the privacy issue. So as I mentioned, most of the federated learning algorithms involve sharing of some updates, typically gradients or model parameters. And the problem with that approach is, though it is not the raw data, if the server has sufficient resources, it can try to do different kinds of gradient leakage or reconstruction attacks. From basically using these updates, it can try to reconstruct the actual data which was used to generate these updates. Right? So then there are different methods to address this problem, such as differential privacy and so on. What we try to do is, okay, the main problem comes when you have a centralized server coordinating all these activities. So why not go for a completely decentralized approach? But in this case, how do you preserve the privacy? So that is where we use the concept of fully homomorphic encryption. Right? So what happens in this scenario is you have multiple participants, they are trying to collaborate. So it's a mutual knowledge distillation kind of scenario. So each of these participants is a teacher to the other participants. So now the problem becomes, how do you distill knowledge from one participant to the another, and without leaking your private data? So we use this concept of fully homomorphic encryption, or FHE. So you encrypt your data, and then you can actually publish your encrypted data. Since you are the one encrypting it and you are holding the key, nobody else knows anything about your data. What the other participants can do is simply get this encrypted data, use their own local models to make predictions in the encrypted domain. So they don't see what are the predictions, but they just do an encrypted inference. And the third thing that happens is you need to somehow distill the knowledge, right? So for that, you need to compute some distillation loss. So we also show that this distillation loss can be computed fully in the encrypted domain. So which means the participant, let's say you have participant 1, the participant 1 just publishes his encrypted data and also an encryption of its own predictions on this data. And the other participants can just make their own predictions and compute this distillation loss in the encrypted domain and return it back to the participant 1. So then the participant 1 can actually go back, decrypt the loss alone, right? So they don't get any other information, they just decrypt the loss and use it for the distillation process. So one of the key challenges here is, how do you compute the loss in the encrypted domain? So we, in this work, we use the KL divergence as the distillation loss. And if you can expand on the KL divergence, you can see that there are some quantities which can directly be computed in the encrypted domain. There is this log sum exponential term, which is very difficult to compute in the encrypted domain, because in FHE domain, you can only do linear operations, right? So you can do additions and multiplications, but it's very difficult to do nonlinear operations like exponential and log. So we show that some of these terms can actually be approximated. Actually, you can remove them completely, or you can approximate them. So that allows you to compute the loss in the encrypted domain without sharing any private data. So this work, we try to compare it with the standard federated averaging and the federated averaging with differential privacy. So the thing is, federated averaging usually gives you very good, the numbers reported here are collaboration gain, which means what is the gain achieved by a participant compared to just a standalone model, right? So in this case, we show that fed averaging gives you very good collaboration gain, but as I mentioned, it is vulnerable to these gradient leakage attacks. So our approach, which is known as CapRide, it achieves much less collaboration gain, but then it is much better than actually doing fed averaging plus differential privacy, right? Especially in cases where you have smaller number of clients, because there, in order to protect your privacy, you need to add a lot more differentially private noise compared to the case where you have many participants in the process. So this is more applicable for the cross-silo setting rather than the cross-device setting. So in cross-device, you have millions of clients, and then each client can add a little bit of noise and get away with without leaking any information about their data. But in the cross-silo case, if you really want to achieve good accuracy, you need to add you need to add less noise, which reveals your private data. So this approach works better than fed averaging plus differential privacy. So the last work which I want to introduce is about collaborative fairness, right? So morning's presentation, Mike introduced, right? So you have multiple entities collaborating in a federated learning setting or in a decentralized learning setting. The key thing is, how do we incentivize these participants? And in this work, we are mainly looking at delivering differentiated models. So the incentive is not financial incentives or economic incentives, it's more differentiated models where the clients which contribute more actually get more benefit in terms of more accurate or better utility models, right? So in this case, how do you quantify the collaboration and how do you quantify the fairness, right? So again, we kind of go back to this decentralized learning approach. So what we found is that when you're doing this mutual distillation, you have a local cross-entropy loss, and you have a distillation loss from the other participants. So by looking at the alignment between the two losses, right? So in this case, you can find the cosine similarity between the two gradients. You can actually see which clients are contributing more to the learning of your model, and which clients are contributing less. And then we can come up with a different weighting mechanism. So you can compute a reputation score for each of those clients. And also we can come up with an adaptive sharing mechanism where you can say, okay, if client B is contributing more to my model, then I will share more with B compared to some other client which does not contribute to my model learning. So I will not share any updates with that client, right? So you can adaptively control the sharing, and that improves the collaborative fairness. So one main issue when you're talking about collaborative fairness is how do we measure the fairness in the first place? Right? The standard definition is, okay, the clients who are contributing more should get better or more accurate models. Right? And the standard metric used is correlation coefficient between the contribution and the rewards received. So usually the contribution is measured in terms of standalone accuracy, which means if your client already has a very high accurate model, then it's contributing more to the collaboration. And then the reward is measured in terms of accuracy after collaboration. So in this case, I'm showing a simple example where there are two clients. So you have client 1 and client 2. They have the standalone accuracy. And if you see the accuracy after collaboration, clearly the client 2, which has higher standalone accuracy, has higher accuracy after collaboration. So in the sense of this particular definition, this is a perfectly fair system. But the issue comes if you look at what is happening in terms of the individual participants. So the blue line in the middle is a zero collaboration gain, which means the accuracy before and after collaboration are the same, right? So that is a zero collaboration gain line. And if you see this client on the left gets high positive collaborative gain, which means it's gaining from the collaboration. Whereas the client on the right gets a negative collaboration gain, right? Maybe the worst case is like, okay, it can just discard the collaboratively learned model and then use its own local model. In that case, it gets zero collaborative gain. But then this goes against the notion of fairness, right? So the client on the right actually makes more contribution to the model learning, but only the client on the left benefits from that. Whereas the client on the right, which makes the higher contribution, is kind of punished. So we need to have get algorithms that ensure positive collaboration gain for all the participants. And at the same time, we want to minimize the collaboration gain spread, which means the variations in the collaboration gain among these different participants. Right? So that is the kind of thing that we try to achieve. So we using this previous approach, which I just mentioned, where you try to compute the reputation of all the participants and then adaptively share. So we were able to show that we can get better positive collaborative gain, at the same time minimize the collaboration gain spread by using our approach. So especially in the imbalance setting. So if you have IID data or even heterogeneous data to some level, you can still achieve good positive collaboration gain for all the participants. So the two figures on the left, right? So here the ones shown in red is the local accuracy or the standalone accuracy, and the blue is the outermost blue square, the blue pentagon is basically the Fed averaging accuracy. So clearly in these two cases, you can see that all the clients benefit from the collaboration. But if you go for a highly imbalanced setting where you have some clients which have large amount of data and which are contributing more, and you have other clients which are contributing very little. So you can see that the client with the highest contribution actually suffers in federated averaging. They have a negative collaboration gain. And our proposed approach addresses this issue. So to summarize, basically I'm more interested in designing collaborative learning algorithms for these non-mutualistic scenarios. And mainly there are three issues. One is how do you handle all these conflicting requirements? It's very easy to come up with a scheme that achieves fairness or that achieves that is more robust to heterogeneous data and so on. But there is very thin line between heterogeneity and malicious behavior by a client. So how do you differentiate these scenarios becomes a challenging problem. And then there are inherent contradictions between privacy and fairness, right? So if you want to achieve higher privacy, you need to reveal as little data as possible or as little information as possible. But then that is not always possible if that actually contradicts with your ability to design fair collaborative learning algorithms. Also, there's need for better contribution assessment and practical incentive mechanisms. Thank you.
Questions for Karthik? I'm curious, so you mentioned you built this reputation system. How was this reputation calculated? Is it based on these cosine similarities you mentioned? Or?
Yeah, based on the cosine similarities. So what we do is we take the cosine similarity between your local loss or gradient based on your local loss, as well as the gradient based on your distillation losses. And if they align, then it means that the other participant is contributing more. So you give a higher reputation to that participant.
But is this like pairwise?
Yeah, it's done pairwise. So it's
actually NC2 reputation.
Yes. Yes. Actually, going back to your question, that actually helps in many cases, right? So in real world scenarios, we can find cases where, let's say, one client has a lot of samples about a particular class. Then a different client may have a lot of data, but may not have that particular class. So in those cases, you can actually see the reputation scores, and it actually correlates with all these distribution shifts.
Hi, thanks for the talk. I was wondering, so I liked the parallelism to the biological relationships that exist, let's say, in the food chain. Do you think that they can exist in parallel when we're training in a collaborative manner a single model? And if so, how can we model this relationship? So you talked about mutualism, commensalism, parasitism, and competition. So there might be relationships between clients. Let's say, for simplicity's sake, in the cross-silo setting, where you have like a binary competitive relationship between like two entities, and then you might have like a mutually beneficial relationship between two other entities.
Yeah, so that's why we decided to go for the decentralized approach, right? Where you can actually model these various types of collaboration, right? So within the same setting, you might have multiple parties which have different binary relationships, right? So some of the participants might have a more mutually beneficial relationship, and then some participants might be more parasitic. So how do you kind of handle these scenarios? It's be easier to do it in a decentralized setting rather than a centralized approach.
But are you talking about one versus all or bilateral, like one versus one?
So just following up on the previous question, right? When you build the reputation, you actually build the reputation individually for each of the other contributors, right? So in that case, you can find out which contributors are helping you, which contributors are hurting you, and which one are not harming you in any way, but they're still there, right? So you can do this evaluation at the individual participant level or pairwise level, right? And then that helps you design better algorithms.
Great, thanks.
Okay, thank you.
Thanks, Karthik. So we have about like a 20-minute coffee break, and then we reconvene at 3.
Check, check, check.
This works? Yeah. Can we make this display bigger? Oh yeah, perfect, thank you. So I'm Praneeth, the other Praneeth. I am a postdoc with Mike Jordan at UC Berkeley. Before this, I did my PhD in EPFL. I work in all areas of federated learning, optimization, efficiency, as well as more recently in mechanism design and designing incentives. I'm looking forward to learning a lot from all of you. So today, I'm going to be talking about how to collaborate with friends and foes. That's my title. It's ongoing work, and most of it is done by Marielle, who is a PhD student with Mike. Okay, so first part, how to collaborate with friends. The setting is there are M users, and this is me. So I want to minimize some loss function. I'm calling it L1 of X. There's also a bunch of other users. These are all my friends who want to help me to minimize my loss. But they have different loss functions. They don't have the same loss functions as I do. We've seen all of the work on this talks on personalization today, but I want to take a more fundamental approach about, I don't want to start by assuming any structure. This is all the assumptions I'm going to make is it's a bunch of other users with different loss functions. And the only assumption I'm going to make is that we have unbiased stochastic gradients to all of them with some bounded variance. So as a baseline, what can I do if I'm just on my own? I have access to my own gradients, so I can just run SGD, locally. And suppose I have access to n samples. So all of us, all the participants have access to n samples. We can just run SGD locally. And we know the convergence rate of SGD. It's very classical analysis, and that's roughly around this variance over n kind of a rate. But suppose now I have some other friend who has a loss function L2, right? I want to answer the question, suppose I have infinite access to L2, like I can do whatever I want with L2, how much does it help me? And this is a pretty fundamental question, and it turns out that we can actually answer this question. So suppose I'm defining this quantity delta square, which is the value of the gradient at each other's optima. So at my optima, what is the value of the gradient of L2, and at optima of L2, what is my gradient? So if we define this quantity, we can show that for any algorithm, give me an algorithm, this is a lower bound proof, you can show, I can construct these functions L1 and L2 such that the error on L1 is lower bounded by this sigma square over n and this delta square. So what this means is that if this delta square is large, or if it's anything larger than the sigma square over n, I get no benefit from collaboration. So the takeaway from this is that only those functions with whom I have a shared minima, so that means the delta square is 0, only those are the users which are actually useful to me. There are some caveats. This is up to all this analysis is up to like numerical constants, and you can make additional structural assumptions, but without that, this is like a fundamental result. So this directly imposes some structure on our problem. So clearly what we have to do is do some kind of a clustering, identify all the other users who have the same optimum as me, and then I can use all of their gradients to improve my training. But this is hard. First of all, just the simple, even the simple clustering problem is actually hard. So if we have points like this, okay, this is pretty easy to cluster in the who is green and who is blue. But if the clients are actually like this, it gets pretty hard, right? So we know that clustering is a hard problem, especially when the clusters are close. And this is, we can actually prove this. So we can translate that intuition into a lower bound. So again, the same delta square quantity. Now, even if we do this kind of clustering procedure, so if we identify only the people who have the same optimum as us, we can improve. So that's this 1 over, hopefully there I can get it to work. Yeah. So previously it was just sigma square over n. I can actually improve it to 1 over m. So you do get the speed up. So if there are m other users who have the same optimum as me, I actually can get the speed up. But there's a penalty I have to pay, which is this delta square over sigma square over delta square term. So this is the penalty I have to necessarily pay to identify this cluster structure. Okay, clustering is hard, but I'm not really just clustering. I'm actually learning, I'm optimizing simultaneously while clustering. So more concretely, I suppose these are my set of loss values, right? So we said that you have to group all the clients who have the same shared optimum. So we have to identify which are the green ones and which are the blue ones. And what we have access to is the gradients of the function, noisy gradients of the function along this red line. I only have access to gradients at this, and just by looking at that, I need to sort of differentiate who is who. So I don't, I have to simultaneously cluster while optimizing. So what that means is that, suppose remember I'm user 1, and there's 2 other clients. There's client I and there's client J. Client I is in my cluster, client J is not. So I need some way to just look at the gradients at the point X and tell whether they're in my cluster or not. So I need some bound on this, some handle on this quantity, the gradient between I and me and J and me. Thankfully, we do have such a bound. So this is like a structural proof again. So if all these functions are smooth and strongly convex, then we can actually prove such a bound that there exists some global constants A and B, such that the gradients of the clients which are in the same cluster as me are close to me, approximately, and the gradients of the clients who are in a different cluster from me are actually, they're actually dissimilar approximately. So what this allows me to do, now I can take this theorem and I can use this to actually differentiate between the clients who are in the same cluster, with whom I have a shared optima and with whom I don't. So I won't go into the details of it, but we can basically take all of this machinery and then turn it into an actual algorithm. I'll just tell you what the final result is. So we can actually do some kind of a federated clustering algorithm such that the error on every single user is the optimal speedup which you could hope for, which is this the sigma square over n multiplied by 1 over m, which is the number of other clients who have the same optimum. So this is the optimal speedup you could possibly hope for, plus this error term which you face because of the unidentifiability of the clusters. There's some assumptions on the A and B as well. It's not super clear whether that's necessary. I think it is, but yeah, I can talk about it. Ask me later. So this is oops. There's still a lot of work to be. This is like really like I think a first step into a theory of personalization. If we add more structure to it, like what we were looking earlier, there's some shared representation, or there's some like subsections only need to be personalized. The more structure you add on the problem, you can sort of adapt all of that into these algorithms. Okay. I also want to talk about. I think this was a point raised earlier. How do you collaborate with competitors? So imagine there's 2 firms, Waymo and Cruise, right? They both are providing the same service. They both are doing this driverless taxis, which are both very data intensive. Is there any reason for them to collaborate? So they're both competing with each other. They're both competing for the same set of competitors, customers. Is there any reason for each of them? Ideally, as customers, we want them to share data with each other to improve the service. But is there a selfish reason for them to do it? And the surprising answer is yes. I'll sort of walk you through why that is. I won't go through the formal theory, but just like an intuition. So suppose Waymo has 100 data points and Cruise has 20 data points, right? So Waymo has a much better quality model than Cruise. And what they will end up, so you can use this theory of, I think the field is called industrial organization, to sort of understand what the equilibrium of this game is. So there's 2 competitors and they both have some amount of data. They can provide some quality. What is the equilibrium? The equilibrium, it turns out, is that the one firm will choose to have a high quality model and set a high price. So people who really want this high quality will go to them. And the other firm will end up using a low quality but a low price. So people who don't care about quality that much will end up going to them. So the 2 firms sort of split the market between them. Now, if they fully share data with each other, they both will end up with the same quality model, and they both will end up with a high quality model, but they have the basically this exact same product. So they'll be highly competitive, and what this will do is this will result in them competing against each other and driving down prices. So this is a setting which neither of them wants to be in. So this, they will never willingly, directly compete with each other in this setting. So ideally, the situation they want to be in is where, I'm going to skip this part. Ideally, the situation they want to be in is where there is some amount of data sharing, but not fully. So both of them slightly improves their model. So they both can increase the amount of money they charge, but still, one still has a much better, they still differentiate the customers between them. So more abstractly, we can think that there is a function, utility function of which Waymo and Cruise have, which depends not only on the quality of their model, but also on the quality of their competitors. So each of them wants to maximize their own revenue. So when they work together, there's this concept called Nash bargaining solution, and which says that basically they'll try to maximize the product of these utilities. So this is the framework which actually advocates for, so it shows that there is actually a benefit to collaborative learning even between competing firms. So essentially what all we have to do now is maximize this, find this Nash bargaining optimal solution, which is basically maximizing this utility function. Okay, so are we done now? So we have a utility function. Can we just run gradient descent? And these qualities, of course, depend. There's an underlying deep learning model which is underlying there, and there's some parameters there. So potentially we could just run federated learning on this new utility function. And are we done? Unfortunately not. So what can happen is, so if you just run gradient descent on this thing, what can happen? So in orange and blue is the two firms. So and I'm plotting the revenue. As you run gradient descent on this function, both of their revenues increases, but the revenue for the orange firm increases a lot more, and then suddenly it suddenly increases and then slowly decreases, and eventually you'll end up at the optimal. At the actual optimal of this. So eventually you will end up here, but in the middle you have this spike, right? You have this spike where one firm is way better off than the other, and what will happen is at this stage the orange firm will just drop off, right? There's no incentive to continue. They're only going to lose if they continue participation. So they're just going to drop off. They'll defect. So we have some interesting constraints on the actual dynamics of the algorithm, which is we don't just want to do this optimization problem, which is this maximize the revenue, but we have to make sure that at every step the revenue is increasing, so that both of them will actually stay put and stay throughout the process. So we can. So in this specific case, we can actually do this. We can actually achieve it. You can compute. There is an algorithm, I won't go into the details, which guarantees that at every round, both the revenues of both firms increase, and eventually it will converge to the ideal revenue setting. So this is this result is very specific for the structure of this problem. So we compute what the utilities are for this problem, and then we can show that for this specific setting, we can achieve this. But what I am interested in, and what I hope I want to pose to the, here's some simulations showing this. So this is the new algorithm which comes out of our theory. So the utility for both firms is relatively monotonic, and so everyone has an incentive to sort of stick through. And the way it achieves this is by sort of maintaining roughly the ratio of the qualities. So structurally, that turns out to be what is necessary. But there's a more general question here, which is, So clear, which is this idea of like multi-objective optimization with some do no harm constraints on the dynamics. And I think this is like a very understudied problem, but I think it has a lot of applications. So this problem I want to sort of pose is, suppose there are, that should be a n, sorry. Suppose there are n objectives. Think of this as like fairness, privacy, bunch of constraints which we want, which ideally we would want to improve all of them simultaneously. And we're starting from some point x0, but we have this constraint that at every step of the improvement, we cannot make any of these objectives worse. So in companies, this is a very this is a standard. Companies have a bunch of metrics, and they will only deploy something if it improves all the metrics, right? So these kind of restrictions are very commonplace in practice, that you have a multiple objectives and you want to improve all of them, and you want to iteratively improve all of them. But we also have some notion of an optimal solution, like in this case, it was this Nash bargaining solution. So is this possible? For what settings is this possible? I think this is an open question, and yeah, I'm pretty excited about this kind of research. Any questions?
Okay. Yeah, maybe I missed the motivation. So in the previous slide, when you say do no harm at every step.
I'm sorry, the slides went away. Can we get back the? Oh, thank you. Yes.
Yeah, like do no harm at every step. Is the motivation that one might just stop at that iteration?
Exactly. If you think of these, if these objectives as belong as the utilities of different people, if at some step my objective is getting worse, I'll just drop out of this collaboration.
Right.
So I want to guarantee that every step is actually improving for me.
Right. Okay. Yeah, in certain cases, I guess for gradients it's fine, but in certain cases where we are just doing sampling, we sometimes want to explore, right? Especially areas where we have not explored before that can get us to a better Pareto optimal. Yeah, but doing that might not.
Yeah, it's not even clear if it's a pretty. I'm not even sure if we add this constraint, what is a set of optimum which are reachable? I don't know the answer, but I think that's what makes us such a cool question.
Yeah.
Behavioral economics here too, right? People don't like to know down.
That's true. Yeah.
I mean, you might ideally like it as a central person.
Yep. I agree.
People don't like it.
Yep. Okay.
Cool. Any other questions?
So on the federated clustering part, what was the next step that could build on top of it that you were motivated by? Is it like a hierarchical tweaking of clients?
If you're a theory person, these rates are not tight yet, and the algorithm is also, it's more of like a proof of concept thing than an actual practical algorithm. So I think there's work to be done in just making this in itself complete. But I don't. But extensions would be, this hierarchical setting would make a lot of sense. I think Sam mentioned in his talk, combining this with Byzantine robustness or with asynchrony, all of these are pretty much open.
Cool. Yeah. Thanks.
Cool. Any other questions?
Thanks, Pranith. Any comment on the motivation for contributing a subset of your data set rather than the whole data set in the whole process?
You mean in this setting?
Yes.
Yeah. So this really comes out of the theory of this, and the idea is that two companies never want to have an identical product. They always want to differentiate the product. And if they've shared their entire data set with each other exactly, then they will have the same product at the end. So ideally, you want to, they will be strategic in how they share data. There is a case for a win-win setting here, because by sharing, they can both improve their models. but they want to be sure that after the sharing happens, there's still some differentiation.
Right. I'm talking about the case where Waymo has 100 data, but they share 80% of that, right? And Cruise shares 15, for example.
Yeah, the specific numbers will sort of, it depends on the modeling assumptions you make. That is what will happen. So essentially what they both will sort of bargain with each other and say, you give me X number of points and I'll give you Y number of points, and this way both of our revenues will increase.
Right. And do you assume that this is a zero-sum game or not?
It's not, and that's the only reason why they will encounter, because it's zero-sum in the sense that the set of customers is fixed,
Right.
but it's not zero-sum because they can charge more for a better quality product.
Okay, thanks.
Cool. Let's move on to the next speaker, probably. Our next speaker is Dr. Brian Low. Brian is Associate Professor of Computer Science at National University of Singapore and the Director of AI Research at AI Singapore. He obtained his bachelor and master degrees in CS from NUS and got his PhD from ECE at CMU and Carnegie Mellon University. His research interests include data-centric AI, resource-efficient AI, probabilistic and autonomate machine learning, collaborative machine learning, planning under uncertainty, and multi-agent robot systems. Today he's talking about some data evaluation and incentives. Yeah.
Yeah, I believe at that time, oh, why is this speaking up? Let's see. Okay, yeah. So I believe at that time there's a voice here. Hello. Yeah, yeah. I still hear myself. Oh. Oh, okay. Wow. Anyway, yeah, let me start. Hello, hello, hello. Yes. Yeah, so at the time there wasn't too much work that was done in this area, and in 2019 then, quite a fair bit of work has popped up. I suspect it's not my machine.
It's making noise and it's on mute.
Oh.
It's muted, guys. Yeah.
Hello? Testing. It's from my machine? Yeah. Okay, let me test again. Yeah, it's good now. All right. Yeah. So, what I'll be talking about for this collaborative machine learning is this part about incentives and data valuation. Back in 2018, we were, I actually heard about 2 different companies wanting to collaborate, and to my surprise, they are not friends, right? So this is, however, they see mutual benefits to it. Each party wants to improve their own payoff, but the question is whether they can still collaborate as self-interested agents. Okay. So this is one of the motivating scenarios that many of you have seen. Well, in Singapore, we actually have 3 different hospital clusters, right? And over there would be a central agent whereby it could be our Ministry of Health, right, that tries to coordinate the sharing of data between these 3 different hospital clusters. Now, of course, for each of these hospital cluster, you can imagine that they are self-interested in nature. They want a predictive model that can help their own patients within the hospital, right? But it could be private, right? Those hospitals could be private. Now, this Ministry of Health is trying to help them to build models, right, such that compared to the model of their own, they are able to obtain an improved model by sharing their data with this central mediator, right? And, one of the aspect or perspective that we want to propose here is the notion that if a certain party is willing to contribute data of more value, then in return, that party should get back a model that is better than the others, right? So this is the notion of fairness that we are talking about. I would be more concrete in terms of what that fairness means. Now, some may ask, like, why not the money, right? Why not give out money? Instead, why are we interested in giving back improved models? So especially in the hospital context, I think their interest is actually getting back an improved model than money. Secondly, yeah, sometimes it's, you can ask David, sometimes it's hard to determine what's the budget, right, up front. You're going to tell the one who's going to give the money how much you need, but how do you quantify how much you need? That's going to be hard, yeah? So we look into model rewards. Towards the end, I can tell you about all the various types of rewards that we have looked at, okay? All right, now this is not pertaining to only the hospital setting. In fact, in Singapore, we also have what we call the urban farms, where they can collaborate as well with their agricultural data. Okay, so to summarize, you will see that all these individual parties have limited data, especially in Singapore, we don't have that many patients per hospital, right? Now, however, if you try to aggregate data from all these different parties, it allows you to build improved models. So now, why do these data owners, why do we need to incentivize them to collaborate? Right? Why do we have to do that? It's because often they incur a certain cost to be able to obtain that data. Right? Therefore, they are looking for such some form of rewards for them to participate. And as I've mentioned, we advocate the perspective of fairness, right? Where you give more valuable data, you actually get rewards that are more valuable. Now, I've also mentioned about why we don't want to be monetary in this case, right? I've already mentioned the reasons. And finally, yeah, we want to give back models as rewards. For now, I'll call them model rewards. This is practical, right? Because all the different parties care about getting an improved model. And interestingly, it is freely replicable. That means using the same data, right, you can replicate another model without an additional cost, all right? So this will be what we care about. Now, what may be slightly different from the other talks that you have heard about is that, we are thinking about what are some of these incentives that people may care about that helps to encourage collaboration. So I'm going to name them one at a time, right, and see all these different properties of the various incentives that we want. So 3 key questions in this entire framework. Now, first and foremost, before I can talk about incentives, one of the problems that I face is that now I need to ascertain how valuable is your data, right? That's my very first step. And that's where I needed to talk to David, right? On how do you value a party's data. Now, from my own experience, there's no one valuation method that's suitable. It really depends on the context. That's at least what I've learned. But in this context of the slides, I'm going to show you just one form that many will be familiar with. Then the second question is, after you have valued the data, how do you design a reward scheme, right, to decide what's the value of the model rewards that each party is going to get in order to incentivize them to collaborate? And finally, how do you realize, given the values of the model rewards, how do you realize the model as the reward to be given back to the different parties? So you can see here that these are the 3 questions: data valuation, incentives, and finally, reward realization. Okay, I'll talk briefly about data valuation. And in this case, I'm going to pick one that, at the start, we actually ask ourselves, now if the valuation method needs to rely on a validation data set, isn't this going to be hard across different parties? Why? Because different parties may have different preferences for what the validation data set could be going forward in their future predictions. They may have a different distribution of points they want to predict in. So this is something that seems like it's hard to agree on a certain validation data set. Now, are there other valuation methods that don't rely on a validation data set? Now, one could look at information gain on the model parameters, right? This is where we look at information gain on the model parameters, right, given the data that you have. And the way we value it is like what you have seen there, right? Oops, yeah, what you've seen in this quantity. I'm trying to gain information on the model parameters, right, given the data of the group of parties that contribute that data, all right? Now, the underlying idea is quite simple with information gain or mutual information, right? If your data provides more value to the model parameters, it means that there's a greater reduction in the uncertainty, right, in the entropic sense, Okay? And because of that, through marginalization, you can actually get a better expected predictive accuracy. And hence, this means that your data is more valuable. Now, there are other interesting properties, like, for example, noise actually causes the value to drop, right? So this comes with interesting properties. Now, then what about the incentives? Right, so you have this central mediator who is going to go about valuing the data of each party, and later on, like what David has mentioned to you on the Sharpley value, they are going to compute the individual Sharpley value for each of them. That's denoted by this phi. And then, using that, we are going to decide what's the reward that will be given, right, to each of the party. Now, like I've mentioned, I want to achieve fairness, and because of that, we have to be careful in what we select to reward the party, right, so that it will be commensurate to the value of their data, right? Later, you're going to see how that's done. Right? So this is the overall process, but in order to get there, after I've valued my data, what kind of incentives should I consider, right? This is the one that I tried to list. Okay, so, over here, I'm going to say that the ideal case is that I want all the parties to collaborate in a grand coalition, right? That's the case. And later on, we will see this stability incentive, right? How do we ensure that the grand coalition stays stable? Now, I'll probably skip the first one, right? The first incentive. The second one is efficiency. Now, we want at least some party to be able to get back a model that's as good as the model that's trained on everyone's data. Now, if that's the case, then you know that the data won't be wasted, right? So that's the efficiency. And rationality, this is the one where I think most people care about, individual rationality. You want to ensure that by collaboration or by collaborating, you get a model that's better than your own, right? Now, in this, the R2 and R3 incentive, we have actually modified it from the cooperative game theory perspective, right, for it to fit into collaborative machine learning. Now, finally, the fairness incentive, right, that I was talking about, the more you contribute, the more you get back. So how do I do that? Now, there are a bunch of properties that you can keep adding to make it look like it's more fair, but these are the 4 that we have picked. Now, the first of all is the one where, if your data does not actually improve any model formed by any different parties, then you know that the data is useless, and therefore this party should get back a model of no value, right? Now, secondly, how do we know that two different parties, right, they should be valued similarly? Now, when the value of the data, right, it contributes similarly to models that are built, right? Therefore, they are symmetric. Now, usually with these two alone, you can sort of think, it's fair, right, in this case, but there should be more. How do I know one party is more desirable than another in terms of their data? Right? This is something that we have actually defined in math, but I'm writing the words here. Okay? Now, comparing these two parties, if there exists at least one group of parties where this party's data can improve the coalition more than the others, while everything else stays the same, then we say that this party is actually more desirable. Okay? Now, besides that, we also want to ask the case where, now, how can a party be incentivized to contribute more of its own data? Right? This is the one where we have the monotone property. So if the party contributes more data, it can result in an improvement in the model, right? Then this party should get a higher reward back. Right? That's the monotone property. So with these 4 properties, if they are all satisfied, then we say that it has this fairness incentive. All right? Okay, now the last 2 properties, desirability and monotone, they actually depend on this thing on marginal contribution, which I think David has mentioned before, so I wouldn't go into it. And the outcome is that Sharpley value is going to satisfy the properties that I've mentioned. There's also this stability incentive, right, where we don't want any sub-coalitions to run away and form by themselves, right? So this is the one where you also want to guarantee that the grand coalition is going to stay stable. I won't elaborate about that. but it's possible to check for stability efficiently. Okay, now the last one is what we call the social or group welfare, which is what most people would care about if you're in economics, right? So, however, think about in our case, if I'm able to maximize the group welfare, it means that every party is going to get back the same model. That's equality. That's actually unfair, right, in our opinion, right? So we want to try to give as much as possible, but instead of giving everyone the same model. That's equality. So we try to increase as much as possible, but don't fully maximize it. Okay, now in terms of the reward scheme, what should we use? Previously, I've mentioned Sharply value, but if we are going to use a Sharply value as a reward, it's not going to satisfy the efficiency incentive, right? Because when you try to sum up the Sharply, it's going to be exactly the same as that of all the parties put together, right? Same value as that. But remember I mentioned that in efficiency, we want at least one party to get the best model as the one that's formed by all the parties together, right? So it doesn't satisfy that. So what do? We revise it so that it's strictly proportional in this case, such that the best party, right, that gets the highest reward value is going to get the best model. However, in this case, even though the efficiency is satisfied, rationality may not be satisfied, right? For certain parties, whatever value they get, it might not be better than their own, all right? So what we do is to include a power parameter that's used as a trade-off called rho, right, that we put on top. Right, this is the trade-off parameter. Now, in this case, we can vary rho depending on what you want. If rho is 1, it's going to be exactly that of the Sharply value. That's Sharply fair. But if rho is 0, that's going to mean equality. You give everybody the same model, right? Now, of course, when you give everyone the same model, rationality is preserved because everyone gets the best model. It's stable. Everyone is happy with the same model. But it's unfair, right? So it should allude to the fact that, hey, I should have a rho value that's sufficiently small, but not 0, right? That will still be fair. So this is exactly what this diagram is showing you. In this big box, it's going to satisfy all those efficiency, feasibility incentives. And then what we really want to clock would be this gray region here, where all the incentives that we have specified so far will be satisfied, including fairness, rationality, and stability. Now, if you have a stable solution, then naturally it will be individually rational. Now, of course, that's done with decreasing rho, okay? Of course, we don't want to decrease it all the way to 0. That would be equality and therefore unfair. Now, of course, at the same time, if you decrease rho, it's going to increase your group welfare. Everybody gets more. Now, if your better off agents or parties want to be more altruistic, right? They can actually decrease rho to allow the weaker parties to benefit more. Okay. Now, in terms of how do we realize the reward for each party so that it's commensurate to the value that the value of the data that they have, this is the part where we use a very simple noise mechanism to add to the data. Right? I'm not going to elaborate on that. Okay. All right, I'm going to skip the experiments and go straight to the take-home message. Oops, okay. Now, earlier on I mentioned to you the goals or the various incentives that we want to satisfy. Right? You've seen fairness, individual rationality, something that we can get back as a better model than your own. Right? We also allow you to achieve stability if you control that trade-off parameter to be sufficiently small. Now, we have chosen the path of non-monetary, right? And what we don't have yet, but we have it this year, would be that of an incentive that is not game theory inspired, right? Instead, we look at this notion of the privacy incentive, right? Can we actually give the ability to each of the parties some way of incorporating differential privacy to their own data. And then what's the trade-off when it comes to how does it affect all the other incentives? Yeah? So that's something that we have this year. I can talk to you more at NeurIPS, where we have that paper. So you can see from this list about the various things that we have done. I've mentioned to you that just now by incorporating the privacy incentive, right, that's the one that is in the NeurIPS 2023, right? This is something that we are very excited by because we can have a privacy incentive to be able to, trade off, right, with the other incentives that we have previously developed. Now, there are also other things that we have considered. Like, for example, just now I mentioned no monetary, right? But what if they want to spend some money to buy a better model? That's where we have a trade-off between payoff and model rewards. I've also mentioned to you all the various rewards that you can get. Just now, I've just told you about giving a model as a reward. But what if some parties want synthetic data that's generated from the raw healthcare data? That's the one that you can see there. Now, some of you may argue with me, but you should give everyone the same model and the best model. Why can't you do that? So yes, we have done something like that as well. We call it fair yet asymptotically equal. That means over time, we are always trying to be fair in every iteration, but in the limit, everyone is going to get the same model. So it's able to achieve both, right, in this sense. Now, what's also interesting would be the case that, for some of these algorithms that you have, like federated learning, there will be iterations. And in each iteration, we want to ask, hey, what does it mean to be locally fair? How is it going to affect you in the global sense? So these are some of the works that we have looked at, right, where locally fair can imply global fairness, right? So this is some works that have been done. And finally, right, as an advertisement, this is just out this today, right? We want to also ask the question, what if somebody has the rights to withdraw their data? And that's where we looked at data valuation where it is deletion robust, right? Can I actually compute the Sharpe value prior to them deleting, right? Okay, that's all I have. Sorry. Thanks.
Brian? Cool, let's thank the speaker again then. Do you want to do it? Han is a Nanyang assistant professor in the School of Computer Science and Engineering, Nanyang Technological University, Singapore. Between 2015 and 2018, he held the prestigious Li Guangyao postdoc fellowship. He obtained his PhD from the same department, NTU, in 2014. His work focuses on trustworthy, federated, ubiquitous learning. He has published over 200 research papers in book chapters, leading international conferences and journals. He co-authored the book Federated Learning, the first monograph on the topic of federated learning. His research work has been recognized multiple scientific awards, and today he's going to talk about some auction-based federated learning.
Sure. Thank you. Thank you very much. So I will be quickly going through this topic so we can have some discussion, and most important thing, the coming dinner today. Okay? So I'll be sharing with you something about auction-based federated learning, because for today's talk, I think we have laid enough groundwork leading to such a topic where we know about works that focuses on data valuation, contribution evaluation, incentive mechanism design, and I will put in one piece of the puzzle towards building auction-based federated learning systems. Okay? So here's my contact information. If you have any questions you wish to discuss with me, I always respond to emails very fast as long as I'm on the ground, not flying. Okay? So our work, the works I'm going to introduce today mostly come from our research center, which is founded by Brian's office in AI Singapore. We focus on developing trustworthy, federated, ubiquitous learning technologies, which encompasses areas including trying to interpret various models and processes under federated learning settings where we can't look at the raw data, laying groundwork for some contribution evaluation and data valuation techniques in terms of fairness, how we design incentives, how we design client selection and team building processes in order to offer equal opportunities for people who are trying to participate in federated learning, as well as people who are trying to access data owners who have data to share. In terms of robustness, the focus is wider, trying to take care of attacks and defenses in federated settings, as well as scaling up and efficiency building, especially in the eras where we either face large number of devices or larger scale models that are emerging. So going into the topic of auction-based federated learning, actually multi-agent-based auctioning has been widely used nowadays in internet advertisement auctioning. So whenever you are opening up a web page, there could be an area designated for showing an advertisement. After 1 or 2 seconds of delay, you see the ads being displayed to you based on your taste, based on analyzing your profile with cookies. That's why they are so keen on you accepting cookies in your web page. And also, based on the interaction of thousands of agents, each representing an advertising agency with a specific goal, specific type of target users they want to attract, as well as a specified return on investment they wish to achieve over the long run. And each individual agent representing them would try to come up with a decision in terms of whether they want to compete by giving an offer for this advertisement space and how much they wish to price that in competition for it. And once the auctioneer collected all this information, they will follow a given auction mechanism to determine who is the winner, charge that winner for whatever premium they need to pay, and then display whatever set advertisement that winning agent is supposed to put there. Okay? So we wish to build something similar in multi-agent empowered federated learning system. So when we are talking about federated learning nowadays, when we are doing research, we have various algorithms about how to select clients, how to aggregate models together, how to build personalized models. But before that, we need to determine who should join whom in terms of forming a team to perform federated learning. And auction-based mechanism could be a way to address this problem. And the aim here is that we wish to build a multi-agent empowered system where people don't have to worry about making such decisions manually, They could have their representative agents, each representing their goals, which they express to the agent in terms of some objective function the agent could optimize, and then through multi-agent interaction, the auctioning process could be carried out. So for such an ecosystem, there could be these three types of stakeholders involved. We have always, may not always be, but most of the time we'll need an auctioneer somewhere as a trusted third party who take care of this whole ecosystem, determine who wins, disseminate information, as well as trying to maintain the integrity of the system in case someone eventually would misbehave, trying to find ways to game such a setup. We would have data consumers or model users, sometimes we call them model users, but essentially they are servers in our federated learning lingo, who wish to spend their budget wisely, engage in useful data owners that can help them train models to accomplish their tasks, and do this as quickly as possible, as efficiently as possible. We will have data owners who have data resources to sell. They will also need to commit some local compute resources in order to participate in federated learning. And of course, what their goal is to earn as much income as possible based on their resources they commit. Okay? So for such a setup, if we take an overview of the key steps involved in here, say this, for this case, this would be the forward auction case. We would first see that the data owners would come up with bid requests submitted to the auctioneer to say, okay, I have something to sell. I need to tell the auctioneer some information about my data set. Of course, I'm not going to copy my data set to anyone else. I'm not going to expose the details, but I need to give some meta information, like what kind of data I have, how many data points I have, and what kind of quality I think my data is. And the auctioneer would say, okay, I now get your bid request. Now I can do information dissemination about this bid request. And I know someone having a resource to sell. Here, we can do a lot of algorithmic research in this area to see, okay, the information dissemination doesn't have to be broadcast to everyone involved. We could do some kind of control here to say, okay, based on observation of previous interactions, the auctioneer might expose this information to select groups of buyers in order to equalize the chances of buyers accessing high-quality data owners over the long run in order to maintain some sort of a fairness objective. Okay? Once information is being disseminated to model users or data consumers, they will say, okay, I look at this data resource, look at my budget, look at my goal. Do I want to bid for this person? If yes, how much I should bid for this particular person in competition with potentially other buyers. And when this information is eventually all coming back to the auctioneers, they would follow a certain auction mechanism to try to determine who wins this data owner. In some cases, one data owner could be potentially multitasking. They could potentially, if they have enough local compute resource, if they can manage it efficiently, they might be simultaneously engaged in multiple training tasks in federated learning. That's also possible. There's another level of complexity we might consider. The type of interactions currently being studied in the AFL literature can be divided into these three major groups. You have the reverse auction, which is a sort of a simplified case where people assume there's only a monopoly market. There's only one buyer in the market. And all the sellers, they're trying to compete against each other to lower their bid so that they can attract this buyer's interest to getting selected. That's the reverse auction case. Forward auction is slightly more realistic in this case. We say, okay, we acknowledge there could be multiple buyers simultaneously competing for the same pool of sellers. And then in that case, it would be the buyers who would need to come up with their bid to try to outbid each other in order to attract from the same pool of data sellers. There could be cases where we can engage in combinatorial auctions, where the data sellers, they could band together to say, okay, maybe we band our data resources together into a packet, into packages of different data resources that can be particularly valuable for certain more complex tasks. for example, that requires multiple modalities of data. They can sell this bundle together for bidders to compete for. That would be combinatorial auction case. Of course, there would be cases where reverse and forward auctions are being combined together. Both parties are trying to bid against each other. That would be the double auction cases where theoretical optimalities is more difficult to analyze. So with that in mind, I will quickly go through some of the representative works that we have participated in these areas. So most of the current available works in the area of designing multi-agent system-based federated auction-based federated learning is focused on serving the purpose for the data consumers, serving the request for the model users. So for this work, this would be a simple starting point where we try to get all these automatic steps done. We build agents that can take previous bidding data as the input to try to see your winning track record from your previous offerings, and then try to use reinforcement learning to see how I can adjust future bids that I want to put out for attracting, maximizing my chance of winning. That would be a simple starting point. And later on, people talk about, okay, maybe in those kind of works, not only just one work, in that category of work where we focus on automating the process, they start by thinking about maybe we spend our entire budget in one go to assemble the entire team and then start training. That may not be the most wise way to do things. Maybe for your instance, when you're trying to hire people, most of the high-quality data owners, they are fully engaged in other tasks. You have to bid for low-quality data owners, or maybe in that case, a lot of other model users are trying to compete for the same pool of data owners together with you. The level of competition is too high. So in the second category of work, people start to think about maybe we do it in a multi-session way. Maybe we don't spend our entire budget in one go. Instead, in planning-based approaches, they're trying to pre-plan. So how many chunks should I divide my budget into? And then they try to minimize my chance of being engaged in very abrasive competitions with others. So in this kind of works, you would have to determine in advance how many different chunks I want to divide my budget into, which may not also be flexible enough. So there are other works that emerging that is thinking about what if we model this whole process as a hierarchical reinforcement learning process over time, so that in each point in time, we would learn to determine what's the percentage of the total budget I want to utilize for this current session to hire the number of people that I need to engage in training. Of course, along the way of engaging people, you don't wait for the entire team to be assembled before you start to train. Instead, once you have a few, you start to train and you monitor whether the model itself has achieved the level of performance that you target, whether you can stop hiring others earlier in an attempt to save more budget. There could be also other opportunities where we can do without a centralized auctioneer, because the centralized auctioneer could be a central point of failure as well. So in this case, we also investigated in this platform about what if people are related in a network of trust or network of acquaintances. Nobody knows everybody else. Each body knows someone else who can potentially propagate information about your intention of initiating a federated learning task and helping you find other potentially useful data owners through a referral network, something similar like this. When you go through a different referral paths in order to eventually find out who can potentially be the most useful data owners for you, and they can win auctions through this way. And of course, in that way, you also need to take into account the referral cost that you need to pay for information dissemination in order to reach your target users. So for the auctioneer part, there's some work, but for the auctioneer part, they're not really concerned about optimizing the payoff for either parties involved. They're mostly concerned about performing certain internal governance within this environment. For example, in this work, we're talking about the information dissemination stage, about trying to achieve fairness among the bidders, among the buyers. So in this case, we use some sort of a tracking approach based on Lyapunov optimization to track the level of regret that the buyers have accumulated over previous rounds of auctioning. If they fail previous rounds of auctioning, we might add some more regret on that, on their queues, so that over time, we would also take this into account to say, okay, this person has repeatedly started to bid for data owners, but due to either budget limitations or some other unforeseen circumstances, they never really got what they really want. So eventually, at a certain point in time, we would try to direct information about high-quality data owners' availability towards those smaller selected groups of data owners, buyers, to maintain some sort of fairness. And in this work, we are thinking about extending that situation because that kind of situation, where we talk about taking regret into account, is akin to a prior-based auction mechanism, which we know prior-based auction mechanisms, they are open for misbehavior, open for people to game such a system. So in this case, we try to look into how we can break up potential collusion rings in such an auction system. We would deploy certain spy agents from the auctioneers. We call them bar agents, who essentially they get attached to each of the bidding agents from the buyers to try to learn the patterns of bidding over time and ascertain whether they are potentially colluding together to try to depress the bidding prices in an attempt to leverage such a system. That's pretty much the current situation about multi-agent-based federated learning through auctions. So far, we don't see any work that's designed for the data owners yet, but that's an area that we can focus on. Just a little bit of final advertisement at the back. We have a workshop coming up in New Rips, 16th of December this month, talking about federated learning in combination with the foundation models, large language models. Very interesting work already accepted, 38 papers. We can take a preview about what people are working on. If you miss this chance, don't worry. We have another one coming up in Singapore this time during WWW. Same topic. If you are interested, deadline is 5th of February. There's still a lot of time. Also, if you are really interested in going to Japan, we have another special session on this topic in IJCNN. Thank you very much.
Thanks, Han. Any questions for Han? Cool. Then,
is there such an auction set up right now? This kind of auctions for data. Do you know of any?
I have to take some slides out of the stack to fit in the time. We have not as complex as this one, but a basic auction-based federated learning system set up in collaboration with the ENN Group, which is an energy trading company in China. They have a lot of subsidiaries as well as companies that are collaborating with them with data to be shared, mostly about energy trading. They talk about procurement of gas for power generation, and they need models to predict demand for gas at different times, different areas. And we have sort of set up a very simple auction-based multi-agent trading system with them for trial. We have a hierarchical incentive structure deployed with them for trial over the past 6 months already. There's a paper coming up in IAI this year, and deployed application track about this. So very simple approach, but the result is very interesting. They use a little bit of budget, like 60,000 yuan in China, but the incentive actually is directly disseminated towards people who are working in the front line to try to incentivize them to improve effort in terms of data collection and cleaning and labeling. And we can see that they get really excited about having such an opportunity. It's very novel to them. And we were able to improve the model performance by like 12 percentage point. And on the best day, the model can save the operation about 120,000 yuan in terms of gas procurement cost. So there's something starting to take shape over there. And there might be others I may not be aware of. Okay. There's another question at the back.
Alexei Tumanov, Georgia Tech. Very interesting work. This is a very sensitive microphone, sorry. Very interesting work, and it's really exciting to see the implementation of actually some of the ideas that Mike Jordan was talking about, like in 2019, essentially developing economic models around the data producers, data consumers, and as well as the models that are being trained on top of that. One of the challenges there is to actually come up with a declarative taxonomy for the data sources. Because you actually need kind of the auctioneer to be able to perform this matchmaking process, which means that you're dealing with some sort of a declarative schema on both producer and consumer sides. So what is the state of the art there? I'm trying to get a sense, like, are you moving beyond just specifying data sets, which are, or some sort of nomenclature for the data sets these data sources represent, or can we move past that point and have a much more involved and much more meaningful taxonomy for data sources?
Yes, that's a quite important question. So I know of some work in that area. Provenance about data is one area where we put descriptions on the data, but there is a branch of work in contribution evaluation which is based on trial and error. So they give some opportunities for people who are they are about to hire, using a sandbox to perform trial, let them join a few rounds of training to see the real impact of the data set on the model performance. And from there onwards, they either engage sharply value-based contribution evaluation, which is hugely computationally costly in that case, because you still have to think about retraining models, combining different submodels together. There's a line of work branching from there, trying to improve the efficiency of this by performing pruning. And also, that's for the horizontal federated learning setting. In the vertical setting, you're talking about not only not data samples, but about the features. People are coming from different business verticals. They are holding data from different features. So there were works coming up trying to perform feature selection and using the number of features being selected eventually for model training to training the vertical federated learning models to determine the contribution from the users. So on top of letting people declare what kind of data quality it is, people are starting to perform trial and errors or through reinforcement learning to really try to see how their impact on the model is. And some even combine that with some sort of a reputation mechanism as a retribution. If you claim this kind of a contribution after we tried your data set, doesn't really match that, there's some consequence on your reputation, which is taken into account for future engagement. Of course, there's also the field of contract theory, where we can design different contract structures for people to choose different contracts, and then that will also have consequences if they cannot fulfill the contract later on. So that's what I understand about the current field now. Thanks.
I think that's also a good question for the panel discussion, because it's a very general question. Yeah. Maybe let's thank Han.
Okay, thank you.